Yeah, sure. My name is Abdel Nasser Tawfiq. I'm professor of theoretical physics. I'm holding two Doctor of Science degrees. The first one I have obtained from Uzbekistan in 2012, and the second one I have obtained from Russia, 2024. I'm also holding a PhD or Doctor of Natural Science from Germany in 1999, which is equivalent to to a PhD. I have been working in Germany for many years, and I have been also at various universities in Germany. Recently, I'm in Cairo, where I'm right now staying. I'm managing the Egyptian Center for the Theoretical Physics, which was established in 2008, and it was classified by UNESCO and the Third World Academy of Sciences as one of the Center of Excellences in the South, where we are eligible to run some common program with UNESCO and the Third World Academy of Sciences. I'm doing theoretical physics in the sense that I'm interested or specialized in particle physics, high energy particle physics, where I have been working for many years. Recently, or not very recently, but in the recent years, couple of years, yeah, I have also have been interested in cosmology and also the general relativity. Currently, I'm trying to join all horses and to concentrate on the very old problem of unifying quantum theory with quantum mechanics. This is a main problem which we are facing in science since the early days of general relativity and quantum mechanics. The problem is that both theories are very fundamental, are very correct, but they are very different from each other. Yeah. And this represents a kind of dilemma, because we couldn't understand, or we couldn't order how two different theories are excellently able to describe one thing, which is the nature. Yeah. This means either one of them is not correct, or both of them are not correct, but we are very sure that both of them are very correct. The problem is that what we have done over the last century is that we convinced ourselves that each of these theories is limited to some scale. General relativity is limited to large scale, and quantum mechanics is limited to low scale. But this is not the ultimate solution for the problem, because we're still facing problem in both theories. Yeah, and I was trying to solve the problem. I'm not the only one who is doing this, and also there are a bunch of brilliant minds over the last centuries who also attempted to solve this problem without success. I think the problem is that there was many new progress which we have achieved in the recent years, which might allow me and my colleagues in the current days to give this attempt and a chance to be done. Yeah, the problem or the approach which I'm proposing is that I'm trying to quantize general relativity using some geometric approach. Yeah, because the theory in its very nature is a geometric theory. The version which was proposed by Einstein was a classical approximation of this geometric theory. What I'm trying is to relax this approximation a little bit. Yeah, and I think the paper I sent to you deals with this topic. Yeah.
Yes. So my first question is, how did you get involved in this project, and what inspired you to study these quantum conditions?
Actually, all people who are working in particle physics, in high energy particle physics, when they try to explain what is this discipline, why we are involved in, we used to reply by the following sentence. We do this because we would like to understand the universe in its very early stages. Yeah, I just try to ask a question. Yeah, how can we understand the universe in its very early stages? Yeah. Um, is that only by doing experiment, high energy experiment, or calculations, or modeling of or using high energy particle physics? Therefore, I was attracted to this topic. Yeah, I was just trying to answer this question. Yeah, how the high energy particle physics or cosmology is related to cosmology. Yeah, therefore, I'm now deeply involved in it. Yeah.
So my second question is, what experimental setups or observations might validate predictions made by the QCC? Are there phenomena in astrophysics or particle physics that could provide direct evidence about this?
QCD has many theories, many experiments for all high energy physics experiments, including the LHC experiments, including the REC experiments, including the future experiments, for instance, FAIR in Germany or NICA in Russia, or other experiments are devoted to support the QCD. The problem with the quantization of general relativity is for us new land. We don't know exactly how we can confirm our prediction empirically or experimentally. We don't know exactly because this is very new land. Yeah.
Okay. So how does QCC redefine the concept of space and time? Could it lead to a fundamental revision of how we perceive reality itself?
Um, yeah, currently we understand that the space-time, which was coined by Einstein and actually by Lorentz about more than a century ago, represents the reality. And what we are doing in physics, including QCD or any other discipline, takes place in some space-time which represents the reality. But when we go to the quantization, as I'm trying to do this, we go to a higher dimension, which is eight-dimensional, including the four-dimensional space-time, but we have extra four-dimensional for momentum space. In this situation, the space-time might no longer represent the reality. We have to deal with some relative localization, or which means that the reality is relative, is no longer absolute reality as we are taught by Einstein theory.
Okay. How does QCC compare to other approaches like string theory or loop quantum gravity in unifying quantum mechanics and general relativity? What makes this method unique?
Its geometric nature that makes it very unique. Loop quantum gravity proposes some quantization, but limited to area of volumes. Loop quantum gravity doesn't touch the length, which we urgently need in general relativity. Quantum field theory quantizes all fields, including gravitational and other fields, but so far are not very successful. Yeah. What I claim that the quantum conditioned curvature, which just prompt from the approximation or from the attempt to quantize general relativity, might be the explanation of quantum gravity, because I see in my calculation, in my estimation, that I have two types of curvatures there. the conventional ones, which are very similar, which are the same as Einstein's predicted, yeah. But I obtained additional curvatures, yeah. These additional curvatures, yeah, have quantum nature, and they are very distinct from the Einstein's curvatures, yeah. This might be this is the manifestation of quantum gravity, because in general relativity, as you know, when we speak about curvature, we mean source of gravity. This means when I obtained additional curvature, it means I obtained additional sources of gravity. This additional source of gravity seem to be quantum, has a quantum nature, but also they are essential and intrinsic and real. They are not artifact prompted from some coordinate transformation here. This means we have to take this additional curvature, this quantum condition curvature, into account when we try to expand the validity of general relativity to cover the entire scale, not only the large scale.
In what ways could QCC reshape our understanding of black holes and singularities, where both quantum and general relativity effects are significant?
Actually, we have studied its impact in black holes, and we realize that the singularity in black holes, or even in initial universe, could be removed. It means this problem of singularity might not be the case if we quantize the general relativity, and this depends on the nature of this quantum condition curvature.
Okay. Could QCC provide insights into the early universe, such as the conditions during the Planck epoch or the nature of cosmic inflation?
Sure. We have done this study already. We studied the universe, and we take into account various solutions for the general relativity, including the simplest solution and up to the most reliable or complicated solution for general relativity. With solution, I mean the evolution of the universe. Yeah. In all these solutions, we have from general relativity, from Einstein's general relativity, the problem of singularity and so on. But when we apply the quantization, this quantum condition curvature, yeah, we see that the singularity could be removed, or even could be regulated. When we have a paper which has this title, yeah, the regulation or attenuation of singularity in initial universe. Yeah.
Okay. So next, I would like to ask, how might QCC interpret phenomena like dark matter, dark energy, or gravitational waves in a way that differs from existing theories?
This is a very good question, actually, but we didn't study this question so far. But we are planning to do this. Yeah, we don't know exactly what would be the impact on dark energy or dark matter and so on. So far, we limited our study to normal matter, to the baryonic matter, and we compare with the Einstein general relativity. It means we don't assume any additional condition or add any ingredient to the setup or configuration proposed by Einstein. We do this intentionally because we would like to compare with Einstein theory. Therefore, we didn't modify the theory of Einstein. We take it as it, and just we add the quantization on it. What we obtained so far is additional curvatures. Other structure could be also, we see from our equations that we have what we call connections. We have what we call geometric structures. Additional curvature, additional connections, additional geometric structure which might be, I mean, so far we don't know their nature, yeah, but might be this, might be all these additionals or this new phenomena which we observed in our equation could be used to interpret critical phenomena, might be including the dark energy and matter and so on. Yeah, but actually we need to investigate this intensively. Somewhere. Yeah.
Okay. So moving to the last questions, one of my questions is, what are the next steps in the development of QCC? How do you envision its role in the broader scientific quest to unify the fundamental forces of nature?
Actually, so far we are aware of some mathematical problems or challenges we have in this approach. I mean, the approach I introduced so far is to some extent approximated because of the huge mathematical challenges we are facing so far. We need first to resolve all these challenges, mathematical challenges, so that our approximation becomes free of our theory becomes free of approximation. This is the first step. The next step, we can do all stuff which have been done over the last century. We can try to study, for instance, the gravitational wave. We can to study what impact would you have on phenomena like gravitational lensing. We can study all, as I said, all stuff which have been predicted or estimated by the general relativity over the last century. So far we have to be sure about our approach, about our theory. The theory is, as you might imagine, very complicated. The mathematics is very complicated. We have to first to resolve some problems. The way to do this is that we have to collaborate with other people. And actually, we are doing this. I mean, we are collaborating with people from all over the world. I mean, with experts from all over the world. And we see the great resonance that our theory or approach gain at their ends. And I think we have some plans to try to propose some projects to resolve firstly, as I said, the mathematical problems, and later on we move to study further phenomena and make predictions. Maybe we could be able to propose some empirical or experimental confirmation for the theory.
Okay, great. And my last question would be, did you encounter any unexpected surprises in your study of QCC, and some good or bad surprises that you were not expecting?
Actually not, because I was, as I said, I was very careful. I came to this topic after long experience which I have in doing research, conducting research, publishing papers, and so on. Therefore, I have to be, or I am actually very careful, with the estimation, with the derivation of expressions and equation and so on. And the resonance which I have received from the referees in prestigious journals when I submitted papers, it's very encouraging and convincing. I mean, I don't receive any critical message about our approach. Just people are just the people or the colleagues or the experts or the referees are they want to have results which needs much more time to research. I mean, they ask about details which we didn't manage to study so far. But the approach itself, the theory itself, looks to be welcomed in the community.